Hey guys, girls, it's Monday again, so we're going to do another beginner's lesson, and this time we're going to talk about transistors. So these are a type of semiconductor device. Hopefully you watched the video last week I made on diodes, where a diode is effectively a two-terminal device. It has an anode and a cathode. So a diode, basically, the symbol is like this. This is the anode, this is the cathode, and it passes current in the direction of the arrow in the symbol, yeah? So this is a diode which only passes current one way. Transistors are a three-terminal device, so they have three legs on them, three terminals, three pads, if you're talking to SMD. And basically transistors fall into two broad categories. You have bipolar and you have field effect. Field effect, yeah? This field effect sometimes what you think like MOSFETs, for instance, you will have hopefully heard of. Anyway, this one we're going to be talking about bipolar transistors, and we'll do field effects on the next one. Okay, so what is a transistor? Well, it's a three-terminal device, and it has three terminals called base, collector, and emitter. Yeah? And what I'll do is, as I've done before, we'll talk about pipes and water, yeah? Because there's something about water and pipes that just makes this so easy to understand. So let's look at what a transistor does, yeah? Imagine we have a water pipe, yeah? And in this water pipe, it's a circular pipe, yeah? And inside this water pipe is a disc, yeah? That can be moved in and out by a lever. So when we can move the disc outwards, the water can flow. The further out the disc is, the more water flows, yeah? Now, let's imagine we have another smaller water pipe, yeah? And in this one, we have, let's put it a little bit further over here, we have a valve, a flap. So the water's flowing this way, and the water pressure causes the flap to lift up to allow the water to pass. And once the pressure becomes enough, the full amount of water that could possibly flow through this thickness of pipe for the pressure flows through. So this flap here is hinged, yeah, and it has a lever on it, okay? And then we have here a pulley, you know, a pulley wheel, and we have a cable. Kind of like a solid type cable, like going to gearboxes and things, yeah, a rigid cable. So if there's no water flowing down here, then the valve, the flap, is closed, yeah? And when water starts to flow down here, it pushes against this flap. And there's a certain pressure, when there's enough pressure, this starts to open, yeah? So as this opens, the lever pulls on this cable and pulls this one outwards, yeah? So you get a little bit of water coming through here, and you get water coming through here, but you get more coming through because it's a wider pipe. Okay, so if you're a little bit coming this way, you get a proportional amount, but more coming that way, yeah? And as you increase this pressure, this flap pushes further open, so this pulls further down, this pulls further out, and eventually you'll reach a point where this pipe now is at its full flow, yeah, for the width of the pipe, and this flap is fully out, so this is now at full flow for the width of the pipe. And you can see that a small amount of water flowing here controls a large amount of water flowing there. Yeah? The water flow will depend on the pressure. How much pressure, yeah? If the pressure here, which by the way, doesn't have to be the same water source, this could be a much higher pressure source, yeah? In other words, more volts if you think of it in electricity, yeah? When the pressure here reaches a certain amount of volts, this flap will lift. And once that's happened, a little bit more volts, there's more and more, and you get more current flow in that way. So that's your analogy, that's your water flow. Right. Let's have a look at it as a transistor. So keeping that in mind, yeah, we have a transistor. There's two types of bipolar transistor. I'll draw one first and then we'll look at the other one afterwards, yeah. So it has three terminals. One terminal is the base. This is this, yeah. This is the controlling flow, okay. We have a collector and we have an emitter, okay. And the arrow on the emitter points in the direction of the current flow, yeah, the conventional current flow. So that is a transistor, that is that pipe, okay. This is the emitter and this is your collector. Often we call them B, C, E, yeah. Now one thing might come to mind, I hope it does come to mind actually. You're thinking, well, actually, why is that called the emitter? Because, like, the water's coming from here. It's coming from the collector and going to the emitter. Shouldn't it kind of, like, go the opposite way? Like, from what's emitting to what's collecting? And the reason for that is conventional current from positive to negative, yeah, is wrong. Conventional current is completely the wrong way round. This is because scientists in the mid-1700s, when they effectively discovered electricity, they thought it flowed from where there was an excess of it to where there was not an excess. There wasn't enough of it. So plus to minus, that's what they thought. But in around sort of like 1890 odd, when they discovered the electron, they actually figured out that the electrons go the other way. So electron current flow is the opposite direction to conventional, yeah? And this is conventional current. I should have left enough room on the paper to fit the word in, yeah, conventional. This emitter and collector is referring to the electron current. You don't need to know that to repair this stuff or to understand it. I just thought I'd tell you in case you think, why is the emitter called an emitter when it's effectively collecting? And that's why. Okay, so that's a transistor. Now, a transistor effectively, one moment. So, as I mentioned before, the transistor, bipolar transistor, is a semiconductor device. Just out of interest, something else interesting, you don't need to know. The word transistor comes from two words joined together. It's a transfer resistor. Yeah, that's where the name actually comes from. Okay, so they're made of silicon, doped silicon, in the same way as a diode is. And we have three layers of silicon joined together, so there's two junctions, yeah? And we get P-type silicon and N-type silicon. So N-type silicon has an excess of electrons, and P-type silicon has an excess of holes. We talked about this on the diodes tutorial. You can always go watch that. So it makes sense. There's two ways to put these things together. We can either have N-type silicon with P-type in the middle and N-type there, yeah? Or you could make it like this. So you have P-type, N-type in the middle, and P-type there. And in actual fact, you can do both of these, and they will both make you a transistor. This one, the middle junction, this is the base, yeah? And you have collector, emitter, okay? And in this case, the N is the base. Collector, emitter. And these two types, strangely enough, this type they call NPN, and this type they call PNP. So that makes that easy, yeah? That's the two types of bipolar transistor that you get. Okay, so what is the difference between these two types, if you like? Well, it's to do with the direction of the current flow and the symbol. This symbol I drew you here, and I said this is a transistor, this is an NPN transistor, okay? If you have a PNP transistor, it's drawn like this, with the arrow pointing the opposite way. Okay, and in this case, current, conventional current, flows from positive to negative, whereas in this case it flows from positive to negative, the other way around. Okay. I mentioned before, remember the water pipe, yeah? You need a certain amount of pressure to open this flap, yeah, to start opening. And then the electricity, the pressure is the voltage, yeah? On the transistor, the voltage between the base and the emitter that's required to start opening this is around 0.6 volts. Okay? Once it starts to open, it doesn't take much more voltage to open that fully, yeah? So you might find it starts opening at 0.6 and it's fully open at around 0.7 volts. It might be 0.8, depends on the transistor, this might be 0.55, but that voltage there between 0.6 and 0.7 is what it takes for this to be closed, so nothing's flowing. This disc is pushed into place to be fully open and this fully flowing, yeah? A very small amount of difference on the base. With a PNP transistor, by the way, because it's all back to front, the base has to be negative with respect to the emitter. Okay? In this case, the base is positive, and the PNP is negative with respect to this. So in this case, the base is minus 0.6 volts to minus 0.7 volts if you measure from the emitter to turn the transistor on. I can't think of any way of drawing that using water unless we have like antimatter and anti-water and anti-valves, but that is how it is. So basically that's what a transistor does, and the schematic symbols for them, and the two types, NPN and PNP. NPN is by far the most common one, yeah. PNP, you tend to find them more in audio circuits where you have both of these working together. So NPN is the more common. I mean, you sometimes find PNP as well. So yeah, let's have a look at some transistors, I think, now. Let's have a look to see what they look like. So we'll look at first at some through-hole transistors. To this, I'll just zoom the camera down from the overhead so you can see a bit easier. Okay, so why use the overhead camera when we can use a microscope, I thought. Haha, far better, eh? Okay, so these are through-hole transistors. They're in like an epoxy type packaging, if you like, to keep the internal parts, you know, safe from damage or moisture or whatever, light. And they have 3 legs, as we mentioned, and they have part numbers on them. Okay. This is a common shape and size packaging for a through-hole transistor, but they don't have to look like this. I mean, back in the day, older ones often look like this, little tin cans, and sometimes larger size tin cans like this one, yeah. Again with part numbers on them, BFY50, these are BC107, yeah. But mostly these days you'll find this type of packaging again. These have got number on, if you see in the bag, BC337, yeah? So that's what your sort of small general purpose through-hole transistor usually looks like. We also have power transistors, which basically is the same thing, it's just handling more currents and can dissipate more wattage. This is salvage part of something marked B772. Is a slightly bigger one, MJE3055. A bigger one again, TIP35C, TIP35C. So transistors come in a whole variety of shapes and sizes, really. I mean, even things like this here is a transistor, this big tin can, yeah. These large ones, these are power transistors, so they're designed to be used in circuits where they handle a lot of current and dissipating a lot of power. So that's basically what transistors look like. On your transistor you will find a part number. So this one's a TIP35C, for example, yeah? This one MJE3055. This one you'll notice is just B772. And if you look at this one, B621. There's a few conventions you'll see, and I'll just mention these. This last one is KSP2222A. You'll often find different manufacturers making effectively the same transistor. So this MJE3055, you'll also find like TIP3055 and even 2N3055, which looks completely different. It looks like the metal can, but they're basically electrically the same type of transistor, if you like. So you'll often find that. You'll also find a lot of transistors that are marked A, B, C or D. So like B772, you might like C3011 or something like that, yeah, or A2478. These are a Japanese method of numbering transistors, and you'll often find with these that in actual fact in front of the letter on the data sheet is 2S. So that would be a 2SB772. This would be a 2SB721, yeah? Same with this one. This is another KSP2222A. You'll often find that marked as 2N2222A. So to discover the ratings, the value, if you like, and the type of transistor, NPN or PNP, the maximum current and so on, you would need to look up the data sheet, yeah? So let's have a quick look now, like this one here, this B772. And what was the other one? B something or other. B621, yeah? Let's look at those online and see whether we can actually find data sheets for those without putting the 2S in front of them. Okay, just give me a minute, we'll go over to the internet. Okay, so let's look for the first one of those transistors to see if we can actually find it. B621. So let's put that in here. B621 data sheet, yeah? B621 data sheet. Yeah, look, you found it, and you've also found the 2SB. So that's told you, yeah? If you couldn't find it, always try put, if it starts with an A, B, C or D, try putting 2S in front of it and see if you can find a data sheet then. Let's find the other one that was the B. This was the B772. So let's see if we can find that one. B772. It has found the data sheet. Let's see if it is actually the 2SB, which I think it is. B772 data sheet. Does it look like the one in the picture? Yes, it does. So we find them anyway. But that's just like a little trick I thought I'd mention to you sometimes. Yeah, so there it is. So here's a data sheet. So this one is intended for audio frequency power amplifier, yeah, NPN transistor. We have some voltage ratings here, collector current and various other things, yeah. That's really weird, this data sheet, because it's marked these as negative voltages and negative currents, and you normally see that on a PNP device. That's really a little bit strange on this data sheet. What it does say is an NPN device. We can test it. Well, let's test the one we have. Okay, so that's how you look up data sheets for transistors. Just from the part number. There are a few little tricks, as I mentioned, about the 2S in front of them. It will gradually, you know, it'll come to you. Don't worry too much about that. If you're not sure, take a photo of the thing and just stick it on one of the forums. Just say, "Can anybody tell me what this is?" You know. But anyway, let's go back over to the desktop camera. So you can see how to actually find the data sheet for transistors. You'll find that a transistor has lots and lots of different ratings, and some are more important than others. You'll find things like VBE, which is the maximum voltage between the base and the emitter. which is normally about 0.7. You'll find ratings like VCE, maximum ratage between the collector and the emitter. This is, if you like, the maximum working voltage for the transformer across the main circuit. Yeah, this can be anywhere from 10 or 20 volts up to really like 1,000 volts, 1,000 and more. You find high voltage transistors. You'll find the ones that are only up to 20 volts. But the data sheet will give you that information. The other one that you'll often find is IC, current of the collector. Yeah. This can be anywhere from several milliamps, yeah, to many amps, 50 amps, whatever, and it can be as low as maybe 100 milliamps or less. Just mention the current on the collector, by the way, and just something that should be clear but probably isn't until I point it out. Just go back to our water pipe, yeah. Effectively, this is your collector, this is your emitter, and this is your base. Okay, so the current collector is effectively the current that's flowing through the collector. What's the current flowing through the emitter? Is it the same? No, it's not, is it? This bit of water going through the narrow pipe, the control flow, where's it going when it comes into here? Well, it's going down into the emitter, yeah? It's joining the collector flow and adding to it. So, a good example, if the collector current was say 100 milliamps, yeah? And the base current was 5 milliamps, the emitter current would be 105. It's the two together, yeah? And just to mention these weird upside down, back to front, crazy PNP transistors, it's the other way around. The current here flows from the emitter to the collector, yeah? But some of it, the control flow, goes from the emitter to the base and flows back out of the base. So, in this case, if the emitter flow, yeah, collector, if the emitter flow was 100 milliamps, yeah, 5 flowing into the base of the control, only 95 would come out of the collector. Everything about PNP transistors is back to front, and sometimes you have to have a certain type of head to get around them sometimes, NPNs kind of make sense. But yeah, there you go, that's your PNP transistor and the way the current flows. So now we've talked about the current flow. That brings us to the next common rating that you find on transistors. And this one is HFE, the big H, little FE. Yeah, this effectively is the gain, how much gain the transistor has. On our water pipe, in our example, if the base, the control flow, is 5 milliamps and the main flow is 100, the gain is 20, because 20 times 5 is 100, yeah? So in this case, HFE would be 20. Typical gain on the transistor, small signal transistor could be 350, 300, 350, somewhere in that region. Certainly, 100 to 400, they fit into a wide range of values. Bigger power transistors, less, yeah, 20, could be a bit lower than that. So, the HFE, and I don't remember what that stands for. I've looked it up and I still don't know what it stands for. You can go and look at it yourself if you want. That is the gain, yeah, that's your gain of your transistor. The only other really useful parameters in my opinion, there's two. There's wattage, yeah, W. This is how much wattage the transistor can dissipate, yeah. You'll notice that small transistors are just little plastic things, yeah, and then they might dissipate 100 milliwatts or a couple hundred milliwatts or something like that. These big transistors often have a metal tab on them, and the metal tab is designed to bolt to a heatsink. So you put a bolt through here into a heatsink, yeah, and it's often quite a large heatsink, sometimes even with fans on them. So these transistors are designed to dissipate a high wattage, and you'll often find it'll give you the rating without cooling and sometimes with cooling as well. Just on these metal tabs, and these are another type of transistor. In this case, you see the metal tab is actually, you know, the whole thing. So the screw goes through the metal tab, yeah. In this case, the screw goes through the, or the bolt rather, goes through the plastic hole, yeah. So there's an insulator in that hole effectively, yeah. Often behind these, you will find there's a washer, a square washer, sometimes made of a clear material, which is called mica, and sometimes which is a mineral basically, and sometimes like a rubbery, grey, thermal type pad as well. You'll find these days. With ones like this one, you'll often find that the bolt that goes through has a little plastic insert that sits inside the hole, and then the bolt goes through, effectively insulating the bolt from the metal tab like this is, yeah. Now, what you'll often find with these type of transistors is the tab is connecting to one of the pins, yeah, usually the middle pin, which on these transistors is almost certainly going to be the collector. So the collector is the one that has the positive voltage on. So that's why they have the insulating washer between here and the heatsink in a lot of cases, yeah. Unless the heatsink itself is connected to the same voltage as the collector is connected to. So when you're changing these transistors, a couple of things. If there's a little rubbery or plastic washer on there, or there's a little plastic insert where the bolt goes through, make sure you put them back when you replace them. And make sure, change the heatsink compound obviously as well, but make sure you put the insulators back in, which if you don't do that, you're going to regret it. You'll regret it if you don't do it. Okay, so that's a little bit about wattage, yeah? Watts can be from, like, you know, several milliwatts or up to many, many watts, 100 watts or more, yeah, off a transistor sometimes. So as I mentioned, I said there was only one other interesting parameter, and I realised there was two. The other one is the frequency. We'll just have a quick look at this on the internet, and I'll show you this one. So we'll have a quick look at the transistors we were looking at physically, before. This is the 2N2222A. I would say something like it had some other prefix, but it was still the same transistor. It's showing you here, look, this is the package. It's showing you emitter, base, collector, pin 1, 2 and 3, so you know which pin is which, yeah. And it's giving you some ratings for it. So the interesting ones would be the collector emitter voltage, which is 30 on, look, there's an A and a non-A, so it's 30 or 40. The A is 40 volts, maximum voltage. It's giving us the maximum current collector, 600 milliamps. Power dissipation, this is the wattage, PTOS, 625 milliamps. It gives us lots of other parameters that we don't really need, but the interesting ones would be the HFE, yeah, this is the gain. So it's giving you, depending on the input current, the gain varies. It's giving you a minimum and a maximum, yeah, for gain. Now, 2222 or 2222A, yeah. And the last thing it's given is this one, the frequency, the cutoff frequency, effectively. So these transistors are good up to 250 megahertz. Compare that with the big transistor we looked at, yeah, the TIP33C, TIP33C. This one, the 33C, is this one, so it's 100 volts. It can handle 10 amps continuously, 15 amps peak. Look, the base current is up to 3 amps. Let's look for the same one. So the gain we'd expect to be a lot lower because it's a power transistor, and he says a lower gain there. Yeah, typical. Well, you know, he's giving you a minimum and a typical. Yeah. And this thing 3 megahertz, so it's only for low frequency use. And we'll just compare that with a radio frequency transistor, just example. So this one, for instance, is a 3 watt transistor. Gain typically 90, but you'll see that this one is actually good up to like 870 megahertz or more. So transistors are basically made for a job, if you like. And really, unless you're a circuit designer, the only reason you'd be wanting to look these up would be if you're trying to find an equivalent transistor. You know, so you've actually got something faulty and you can't find the right part. Personally, I would say that in that instance, until you become more experienced, I would ask on the internet. You know, again, put a photo up, say this is what I need. Can somebody find me a suitable replacement? Okay, so we've looked at those. Next thing, let's have a look to see what transistors actually do. Yeah, what they're used for.